Hi everyone, welcome once more to this YouTube channel, Best Science Brain YouTube channel. And today we are taking a look at a topic in physical chemistry, derivation of the integrated form of second order kinetics or second order reaction. So this video is meant for students in high institution, tertiary institution, many those in second year and first year, and also those who are doing their remedial courses in postgraduate studies or master degree in chemistry, chemical engineering, or related chemical courses. So we have already talked about second order reaction as a reaction in which the concentration of the reactant in the given rate law is raised to power 2 for a unimolecular reaction. But if the reaction is a bimolecular reaction of two different substances, it means that the sum of the exponents of the concentration terms will be equal to 2. So let's go ahead with our lecture. Before we continue, if you are not subscribed to the channel, if you are not subscribed, kindly move up to the channel's name, then close the channel's name. You're going to see the subscription bell or button. Tap on that icon only once and get subscribed to the channel for more tutorial videos. So let's continue. Second order reaction is a reaction in which the concentration term in the rate equation is raised to power 2, or the sum of the exponents of the concentration terms in the given rate law is 2. So we are defining second order reaction. For better understanding of second order reaction, search this channel and see where we did for the topic rate of reaction and kinetics, and see where we explain order of reactions. Then let us consider a molecular reaction, which is a second order reaction, or a bimolecular reaction in which the reactants are the same substance. Look at that reaction, that expression, A going to product. That is a molecular reaction. Why it is so? Because we have only one particle of A in the reaction, so that's why it's unimolecular. But I can still make it bimolecular by putting 2 in front of A. So it now becomes bimolecular reaction of the same kind of substance. So we are looking at how to derive second order integrated equation for this kind of reaction that is bimolecular of the same kind or unimolecular reaction. So we say let the initial concentration A of reactant A, called A the reactant, be equal to small a in square bracket mole per dnq. Let the concentration of A, reactant A that has decomposed into product after time t be equal to square brackets S mole per dnq. So small a represents the initial amount of A present, and then S in bracket represents the amount of A that has changed to product after some time. Hence, the concentration of reactant A remaining after time t now become A minus S, that is the initial minus what had decomposed. So that becomes the concentration of A remaining after some time t. It then follows that the rate of change of the concentration of reactant A that had decomposed, that is S, is directly proportional to the concentration of reactant A that is remaining after time t, which is A minus S. I repeat, it then follows that the rate of change of the concentration of reactant A that had decomposed, which is S in square bracket, is directly proportional to the concentration of reactant A that remaining after time t, which is A minus S. Turning that statement into mathematical expression, we now say ds over dt proportional to A minus S to the power 2. That power 2 indicates that the reaction we are considering is a second order reaction. So we bring in a constant. That constant is K, known as the rate constant. So introduce the rate constant, we now have the equation now turned to remove the proportionality sign and bring equal to and then K. We now have ds over dt equal to K into A minus S to the power 2. So we now cross multiply. When we multiply, we now have ds multiplying 1 and then A dt multiplying K into A minus S squared. So when we have equation 2, ds equal to K, A minus S squared dt. That brings you, after the multiplication, we now have equation 2. Divide both sides of equation 2 by A minus S squared to separate variables. So divide the S by A minus S to the power 2. Divide K times A minus S power 2 dt by the same A minus S power 2. we obtain ds all over a minus s power 2 equal to k a minus s power 2 dt all over a minus s power 2 dt. Look at the right hand side of the equation. A minus s squared cancel each other. So we are now left with ds all over a minus s squared equal to k dt. That becomes equation 3. So we now proceed to integrate. We now integrate equation 3 with respect to s with boundaries s equal to s and s equal to 0 and t equal to t and t also equal to 0. When we integrate equation 3, we now have this. We will bring in the integration sign to this equation 3. So when we bring the integration sign and the boundaries, we have the integration signs there, as you can see it on both sides of the equation, the right hand side and left hand side. Now for us to integrate this, we need to understand calculus. To understand calculus, you have to revise your mathematics, year 1 mathematics, one semester year 1 mathematics, year maths 101 or 102, and then be able to understand calculus. Or you go and pick your postgraduate student, you pick engineering mathematics by K.A. Stroud and go through integration and aspect of the mathematics textbook. So, but we have a little revision we need here for us to have a better understanding. We say that in order to integrate the above expression, we have to revise calculus in mathematics. Like this expression will have 1 over s to the power n ds. How do we integrate this expression? We first of all change the 1 over sn to indices. It gives us s power minus n ds. Then what do? We add 1 to the power minus n. So look at it on the extreme. S power minus n plus 1. And still divide the numerator by the same power, the new power minus n plus 1. Then plus c. That c is the constant of integration. Taking this example, 1 over s cubed ds. How do you integrate it? We now say convert 1 over s cubed to indices, because s power minus 3 ds. That gives us s power minus 3 plus 1 all over minus 3 plus 1 also, then plus c. So minus 3 plus 1 gives us minus 2. That will have s power minus 2. The denominator minus 3 plus 1 also gives us minus 2. Then you have 2 under, then minus comes up. That's why you have minus s minus in front of s, then plus c. Then we'll take another example that is more useful to us in this integration. We have 1 over a minus k s raised to power n. That k is the coefficient of s. Then ds. To integrate this, we say convert the denominator to indices. It now gives us bracket a minus k s raised to power minus n ds. We follow the same pattern to integrate. We add plus 1 to the power or the exponent. We now have a minus k s in bracket, then minus n plus 1 up. We still divide by the same minus 1 plus minus n plus 1. But we have something under the denominator apart from the minus n plus 1. We have minus k. How do we get the minus k? The minus k is the coefficient of s, the numerator. We have that equation of s on the numerator is minus k. You multiply what you have on the denominator by minus k and then plus c. You get your answer. For example, we have 1 over a minus 5s raised to power 3. To integrate this, to convert the denominator to indices, that gives us a raised to power minus 5s, a minus 5s in bracket raised to power minus 3 ds. And that will give us a minus 5s raised to power minus 3 plus 1. You add 1 to the power. Then all over minus 3 plus 1. Then multiply by minus 5. Minus 5 is the coefficient of s. The coefficient of s on the numerator is minus 5. So you just multiply what you have in the denominator. So minus 3 plus 1 give us, the numerator will give us minus 2. Then minus 3 plus 1, the numerator will also give us minus 2. Then minus 2 times minus 5 give us plus 10. So we have the final answer, a minus 5s power minus 2 all over 10 plus c. You see, we apply this to integrate the main equation. Having revised integration, we now record equation 3 above. Look at equation 3 that we were about to integrate before we went to the mathematics aspect. So we integrate the right hand side of the equation 3 and apply boundaries. The right hand side is k integral dt. So we now have that. The k was brought up because k is a constant. You integrate the t, you get t. So look at the middle expression. So kt. We now bring in the boundaries. That's replacing t with t, replacing t with 0. Look at the extreme expression. K into t, replacing t with t, then minus, then replacing t with 0. So t minus 0 is t. Then t times k gives us kt. So to apply the boundaries or limits, replace the value t with t, replace the value t also with 0 and subtract the 2, then multiply by k. You have kt. Then integrating the left-hand side of the above equation. The left-hand side is this one. Yes. ds all over a minus s squared. So we now have 1 over a minus s squared, pushing the ds off. The coefficient of ds is 1. That will have 1 up. We'll convert 1 over a minus s power to doing this because a minus s power minus 2 ds. So having done that, how do we integrate? We apply what we have learned previously. We're going to add minus 2. We are going to add plus 1 to minus 2 and then divide by minus 2 plus 1. So you see, we now have a minus s minus 2 plus 1, then under minus 2 plus 1, then multiply by minus 1 as denominator. Look at it. Where the minus 1 from? The minus 1, the coefficient of s on the numerator side. The coefficient of s there is minus 1. So that's why the minus 1 is underneath. So minus 2 plus 1 gives us minus 1. Look at the middle value, middle expression. The minus 2 plus 1 at the denominator of the first expression give you minus 1. The minus 1 times minus 1 in the first expression give you 1 whole number. That's what you are having there. So at the end of the day, minus 1 times minus 1 give you 1. So it will vanish. We are left with a minus s raised power minus 1. And a minus s power minus 1 converted to fraction will give you 1 over a minus s. Then we replace s with s, the boundaries, and replace s with 0. So replace s with s, you now have the same a minus s. Replace s with 0, you now have a minus 0. Subtract the 2 limits. You now have 1 over a minus s minus 1 over a. So this is the integrated form of the left-hand side of the equation. We now merge the left-hand side and the right-hand side. Remember the right-hand side got it as kt. So merge them together. We now have 1 over a minus s minus 1 over a equal to kt. So this equation 4 represents the integrated form of a second-order reaction that involves, that is for a unimolecular reaction or a molecular reaction that involves similar reactant. So equation 4 is the integrated form of a second-order reaction or a unimolecular reaction or a bimolecular reaction of the same reactant. So that is it. In this session, we'll move over to calculation of second-order kinetics. So we say, in order to perform calculation on second-order reaction, we need to modify equation 4. You can see equation 4 we got before. So we have to modify it. What do? We say, let the initial concentration at time 0, given as small a in bracket, which is in equation 4. Replace that with small ai, where that subscript I means initial. And let the concentration of the at time t, which is a minus s in equation 4, the first expression, be equal to, replace the thing with a subscript t, which means concentration at time t. So modifying that equation 4, we now have equation 5. This is equation 4 already. 1 over a minus s minus 1 over a. Replace a minus s with at. Replace a with ai. So equal to kt. So equation 4 has been simplified to get equation 5. So taking the LCM of the left-hand side of equation 4. If you take the LCM equation of the left-hand side of the equation 4 and bring the values under a common denominator. So the LCM of the LCM is going to be AT times AI. We join them to one fraction. We now have a small a bracket I minus small at all over small at multiplied by ai equal to kt. That is equation 6. We're going to apply equation 6. It's simplified now to do calculations on second-order kinetics. So we say equation C is a modified form of second order kinetics of unimolecular reaction or a biomolecular reaction of the same reactant molecules. We shall apply this equation in our calculations. Example 1 says the gas phase decomposition of hydrogen iodide given by 1 molecule of HI giving us half molecule of hydrogen and half molecule of iodine, and has a rate expression of K, initial rate equal to K, iodine concentration rate power 2. So from the rate expression, you already know that there is another reaction because HI raised power 2, where K is equal to 30 liter per mole per minute at 443 degrees Celsius. How long will it take for the concentration of HI to fall from 0.010 mole per dN³ to 0.0050 mole per dN³? So this equation or a calculation is another reaction. Let's see how we can tackle that with equation 6. So having done that, we'll go to the solution. Initial rate is K HI to power 2 given to us in the equation. And the reaction is another kinetics because the concentration of hydrogen iodide is power 2, as you can see there. So initial concentration of HI, which is supposed to be AI, we'll now write it at HII because that A now represents the reactant, which is HI. So I is initial, given to us as 0.01 mole, 0.01 molar solution, that is mole per dN³ given to us in the equation. Then concentration of HI at time T, after some time T, which is supposed to be AT in equation 6, we now write it down as HIT as the value given to us as 0.0050 mole per dN³. Our rate constant is given to us also as 30 liter per mole per minute. We now employ equation 6 to solve. Equation 6 that says AI minus AT equal to AT times AI equal to KT. That equation 6. We just modify it. How do we do that? We replace anywhere we see A, we replace it with HI. That's the only difference there. So modify it. We now have this equation. Substitute the given values into the above equation. The values we already mentioned before. The initial concentration of HI is 0.01. The concentration of HI after some time T is 0.005. Then multiply the two denominator HI initial multiplied by HI at time T equal to KT, or K is the rate constant, which is 30, that is 30T. You subtract the numerator 0.01 minus 0.005 will still give us the same 0.005. Multiply the denominator 0.01 multiplied by 0.005 will give us 0.000405. Then equal to 30T. We'll divide 0.050 by 0.00005. We get 100 equal to 30T. We made T the subject, divide both sides by 30. So T now becomes 100 over 30. That gives us 3.33 minutes. So you're going to take 3.33 minutes for the question of the substance to move from 0.01 to 0.005 mole per dN³. Go to example 2, says the decomposition of nitrogen dioxide at 285 degrees Celsius had the rate equation. Initial rate equal to K NO2 in bracket raised power 2. So from that initial rate given to us, that shows that this is second order kinetics because for second order reaction, the reactant will rate power 2. So if rate power 1, that means we're dealing with the first order kinetics. So we now have the equation NO2 giving us 1 molecule of nitrogen and half molecule of oxygen. We are now told that given that the initial concentration of NO2 is 0.020 mole per dN³, and the concentration of NO2 after 2 minutes is 0.00870 mole per dN³, calculate the rate constant of decomposition of nitrogen 4 oxide. The same process we applied before. We now go to the solution. Initial rate is K NO2 in brackets raised power 2 given to us in the equation, and that shows the second order reaction because NO2 is raised power 2. Initial concentration of NO2, which is AI, replace the A with NO2, that gives NO2I is 0.02 given to us in the equation. Concentration after time, the time is given to us already 2 minutes, is AT. So we replace the A with NO2, that gives us NO2T, which is given to us also as 0.00870 mole per Tn cube. The time is 2 minutes. We're looking for K. We employ equation 6 again, but this time around we're going to replace A with NO2 in this equation and modify it. We now have NO2 I initial minus NO2 at time T all over NO2 at time T multiplied by NO2 initial equal to KT. So to the given values, we have 0.020, which is the initial concentration minus 0.00870, with the concentration after 2 minutes, all over the product of the two at the denominator equal to KT. That T is 2 minutes. We're looking for K. So we divide, if you subtract 0.02 minus 0.00870 gives us 0.0113. Then 0.020 multiplied by 0.0087, the denominator will give us 0.000174. Divide the left-hand side, 0.0113 by 0.000174, you get 64.94 equal to 2K. Divide both sides by 2 to make K the subject. K now gives us at 2.5 liter per mole per minute. Example 3 says the gas phase decomposition having iodide HI again by half hydrogen, half more of hydrogen plus half more of iodine. It has the rate expression. So initial concentration of HIAI, that is HI subscript I, is 0.01 mole per Tn cube. The concentration of HI after 1/6 hour is AT, that is HIT, which is unknown. We're looking for it. So the rate constant is 30 liter per mole per minute. The time is 1/6 hour. That is 1/6 times 60 minutes. Converting to minutes, that gives us 10 minutes. So why do we convert the time to minutes? You look at the rate, the K, the rate constant is 30 liter per mole per minute. So rate constant K is carrying minutes. So the time must also be brought to minutes. The unit must be uniform. If the rate constant is in hour per mole per hour, liter per mole per hour, then we leave it in hour. So look at the bracket. So the units of K and T must correspond. So we employ equation 6. Yes, AI minus AT all over AT times AI equal to KT. So all I have to do is replace A with the substance, which is HI, and modify it. So modify the equation. Now have HI initial minus HI at time T all over HI initial at time T minus HI initial times KT. Then substitute the given values into the above expression. So 0.01 minus HIT, we're looking for HIT, that the concentration at time T, all over 0.01 times HIT all over equal to 30. 30 is the rate constant, that is time. Time is 10 minutes. We'll then cross multiply. When we multiply, we'll have 0.010 minus HIT times 1. We still give the same value underneath. Then we'll have 0.01 HT times 300 under. So multiplying, we now have 0.01 minus HIT equal to 300 times 0.01 give us 3 HT. We collect line terms. The HT values go to the right hand side. We now have 0.01 equal to 3 HT plus HT. Then we're going to have 3 HT plus HIT, plus HIT give us 4 HIT. Adding the coefficients, 3 in front of 3 HIT and then 1 in front of HIT, that gives you 4 HIT. Then dividing both sides by 4, we now have HIT giving us 0.01 all over 4. That gives us 0.0025 mole per Tn cube. So that the concentration remain after 1/6 hour. So we move to a greater or a harder part of integration of derivation of second-order kinetics. That is the one that involves a second-order reaction, the biomolecular reaction involving two different reactants. Remember that the one we have studied already is integrated form of second-order reaction that involves a unimolecular reaction or a biomolecular reaction that involves the same reactant. But we're looking at how to derive the integrated form of a second-order reaction that involves a biomolecular reaction. that with two different reactants. So let's go ahead. Let us consider a bimolecular reaction involving two different reactants A and B as depicted below. We have A plus B giving us product, where A and B are different reactants. So you look at this situation. This is a bimolecular reaction involving two different reactants. Let the initial concentration of A be equal to A mole per dm cube. Let the initial concentration of B be equal to B mole per dm cube. Let the concentration of A that has reacted at time t be equal to S mole per dm cube. Also, let the concentration of B that has reacted or has been converted to product after time t be equal to the same S mole per dm cube. That means we assume that the concentration of A and B reactant that are decomposed after some time t are the same, S mole per dm cube, S mole per dm in each case. Then concentration of reactant A remaining after time t becomes A minus small a minus S mole per dm cube. Concentration of B remaining after time t also becomes small b minus S mole per dm cube. It then follows that the S over dt equal to K bracket open small a minus small s bracket closes, that concentration of A minus S all over multiplied by B small b minus S. That small a minus small s and small b minus small s represent the concentration of the substance remaining after some time t. So we will now cross multiply the above expression to separate variables. When we multiply, we have the s multiplying 1 giving us the s under. We have K multiplying A minus S multiplying B minus S multiplying dt giving us K multiplying A minus S in bracket B minus S in bracket then dt. That's equation 1. Dividing both sides of equation 1 with A minus S in bracket then B minus S in bracket. So divide the S by small a minus S in bracket, then bracket also small b minus S, then divide the right hand side also by the same a minus S, b minus S. So you see that on the right hand side a minus S, b minus S will cancel out. We are left with k dt. We now have the S all over a minus S into b minus S, then k dt equation 2. We now go solving left hand side of equation 2 by partial fraction. The left hand side is the ds all over a minus S, then b minus S. Solving by partial fraction, the denominator mainly. You have to go through your further maths textbook to understand partial fraction, but we still did some good work here. How do we solve the partial fraction? We remove the ds and take its coefficient, which is 1. We now take 1 over a minus S then into b minus S equal to separate variables. How do you separate? Separate a minus S from b minus S and then put a plus sign between them. Place unknown letters on top of each of the fractions. So let's place C on top of a minus S and place D on top of b minus S. That gives us equation 4. We're going to look for C and D. That is how to solve partial fraction. So to solve, multiply both sides of the equation with the denominator on the left hand side. The denominator on the left hand side is a minus S and b minus S. So multiply both sides with that denominator. So we now have a minus S. We multiply the left hand side with the same value, the same denominator, a minus S, b minus S. It will cancel out, as you can see on the left hand side. A minus S, b minus S, cancelling out a minus S and b minus S. Then you multiply C all over a minus S by the same a minus S, b minus S. You see a minus S cancel out a minus S. Also, do the same thing with D all over b minus S. Multiply it by the same denominator, a minus S, b minus S. B minus S cancel out b minus S. So having done that, we are now left with the right hand side has only 1. So a minus S multiplied by b minus S cancels us off a minus S multiplied by b minus S, giving us 1. Then the right hand side now has C equal to what remaining there is now b minus S plus then D, what remaining now is into a minus S. That's equation 5. So we have the right hand side cancelling out giving us 1. the left hand side, A minus S cancels A minus S, remaining C into B minus S. Then D, we'll have B minus S, but cancel B minus S, leaving behind D into A minus S. So as equation 5. We'll now go ahead to solve for C and D. How do we solve for D and D? C and D. We now take S to be equal to B. The first expression, C into B minus S, replace S with B. Replace S with B, so we now have C into B minus B equal to A. Then replace S with B into A minus B. So where you see S here, replace it with B. By so doing, we want to eliminate B. So in 1 equal to, we now have 1 equal to, then 0. Well, how come 0? B minus B is 0. So 0 times C give us 0. Plus D into A minus B. So we're now left with 1 equal to D into A minus B. Divide both sides by A minus B to make D the subject. So by so doing, our D is now 1 all over A minus B. We now go back to the equation 6, or equation 6, or 4 rather. 1 equal to B minus S, C, 1 equal to C into B minus S plus D into A minus S. So now we replace, we make S to be equal to A. Previously we made S to be equal to B, but now we make S to be equal to A. So that gives us 1 equal to C into B minus A plus D into A minus A, replacing S now with A. So having done that, we now have 1 equal to B, C into B minus A plus D into A minus A is 0. So D times 0 gives us D. We're now left with 1 equal to C into B minus A. We make C the subject. Divide both sides with B minus A to make C the subject. C now becomes 1 all over B minus A. So we have already found the value of D. D is 1 all over A minus B. How do we find D? In this equation 4, let's go back. That is equation 5. Replace S with B. And then we got D as 1 all over A minus B. We now went back and replaced S with A in the same equation. Replace S with A. We now got C as 1 over B minus A. Then we substitute the values of C and D into the right hand side of equation 4. So this equation 4, where we have 1 over A minus S multiplied by B minus S equal to C all over A minus S plus D minus S. That's the partial fraction we started with. We have gotten the value of C and D. So we now replace C and D with their actual values. So we now have 1 over A minus S multiplied by B minus S equal to the value of our C is 1 over B minus A multiplied by 1 over A minus S. Then D, the value of D is 1 over A minus B multiplied by remaining 1 over B minus S. We have this expression which we call equation 6. So you can see it very well. So having done that, now we are going to integrate the bracketed fractions on the right hand side of the equation 6. We integrate those values in brackets on the right hand side of equation 6. So if we integrate, in order to understand the integration process, we shall briefly revise calculus again in mathematics. 1 over S ds is written as being S plus C. So 1 over A minus Ks, where K is the coefficient of S, ds give us ln A minus Ks divided by minus K. That minus K, the coefficient of S, plus C, that integration constant. For example, if I have integrate 1 over 2 minus 3s ds, will give us minus the natural log of 2 minus 3s all over 3. How do I get the 3? The coefficient of S there is minus 3 divided by minus 3. That way you have the minus sign in front of ln, then plus C. So following this process, We now integrate the values in bracket. Another example is integrate 1 over 2 minus s ds will give us ln 2 minus s. Then divide ln 2 minus s by the coefficient of s, which is minus 1, which now you have the minus up. We now have minus, that minus us you have on in front of ln because divided the ln 2 minus s by minus 1 with the coefficient of s on the denominator there is minus 1. So we now have minus ln 2 minus s plus c. Having understood this aspect of integration, we now apply it to integrate the bracketed fractions on the right hand side of equation 6. So look at the fractions on the right. This is the right hand side of equation 6. 1 over b minus 8, b minus a. Then integrate integral of 1 over a minus s, which is the value in bracket. Then plus 1 over a minus b, integral of 1 over b minus s, which is the value in bracket on the right hand side of equation 6 above. Then if you integrate 1 over a minus s, you have ln a minus s. The minus sign in front of the ln a minus s is the coefficient of s on the denominator of a minus s. Coefficient of s there is minus 1. So you divide ln a minus s by minus 1, you have that minus ln a minus s. Then if you integrate 1 over b minus s, you have ln b minus s. The coefficient of s on the denominator of 1 over b minus s is minus 1. So divide ln b minus s by minus 1, you have minus ln b minus s. Then we have 1 over b minus a in front of the first expression and 1 over a minus b in the front of the second expression. We now apply limits. The limits we apply is taking s to be equal to s and s is equal to 0 to the first half of the expression. We have the first half is cut it into 2. The first half is 1 over b minus a bracket minus ln a minus s. That's the first half. We now bring in boundaries, taking s to be equal to s and s equal to 0. So look at that first half. Replace s with s, we have that, and then we replace s with 0, we have that. So now 1 over b minus a, open the bracket, then minus ln a minus s, minus, and that bracket opens, minus ln a minus 0, bracket closes. So when we solve this out, we now have 1 over b minus a, bracket opens, minus ln a minus s, then the minus here will give you plus. Now give you plus ln a. So having done that, we repeat the above process again for the second half of the above expression. Second half is, go back, do the second half. No, that is not. The second half is this part, 1 over a minus b minus bracket open minus ln, bracket opens again b minus s. That's the second half of it. We apply boundaries to it. So that's the second half. 1 over a minus b, bracket opens minus ln, bracket opens again b minus s. Replace s with s and also replace s with 0. So we now have 1 over a minus b, bracket opens, minus b, ln b minus s, replacing s with s, bracket closes, minus again, then open the bracket, minus ln b minus 0. This time around replace s with 0. So solve out, we now have 1 over a minus b, bracket opens, minus ln b minus s, bracket closes, then plus ln b. Then merging the first half and second half together, we have 1 over b minus a, bracket opens, minus ln a minus s, bracket closes, plus ln a, bracket closes, plus 1 over b minus a in bracket opens again, a bigger one, minus ln, a smaller bracket, b minus s, bracket closes, plus ln b, inside concentration of b, then bracket closes. Then multiply the denominator in the first half of the expression above with minus 1, and the coefficient of the expression in the bracket with minus 1. The denominator in the first half with minus 1. Let's see what happens. Multiply the by minus 1. Denominator of the first half, we're going to have minus b plus a. So the first half is, we have the first expression there is 1 over b minus a, multiply it by minus 1, have minus b plus a, which can also be written as a minus b. Then ln minus ln, okay, we'll say multiply the denominator of the first half of the expression above with minus 1 and the coefficient of the expression in the bracket with minus 1. So multiply the denominator with minus 1 and it turns from b minus a to minus b plus a, which is written as a minus b. Then the coefficient of the first expression in the bracket, that ln a minus s, what I have in front is minus 1. Multiply by under minus 1, we'll now have plus, changing it to plus. We'll now come to this expression here. And then 1 over a minus b, bracket opens, ln, concentration of a minus s minus, ln, concentration of a, then bracket closes, plus 1 over a minus b, b bracket opens, minus ln, then a, b minus s, concentration plus, ln of concentration of b. Having done that, factorize the above expression, we obtain, they have something in common. They now have a minus b in common. We'll bring out a minus b. That is 1 over a minus b. So now 1 over a minus b equal to, bracket opens, ln, concentration of a minus s minus, ln, concentration of a minus, ln, concentration of b minus s plus, ln b, bracket closes. So we'll factorize it. We separate like terms. So what are the like terms? Ln a minus s is similar to ln b minus s. Bring them together. So we now have ln a minus s and ln b minus s coming together. Remember that ln b minus s has minus sign in front of it. So ln a minus s, then ln b minus s minus ln b minus s will now come close to ln a minus s. So we also see that ln b and ln a have no s value. So bring ln b has plus sign in front of it, ln b, and then ln a has minus sign in front of it. Bring them together. So we now have plus ln b minus ln a. We now apply the logarithm rules of subtractional addition to the above expression. And you know in logarithm, when you have minus sign, it turns to division. And when you have plus sign, it turns to multiplication. So we now have 1 over a minus b, ln a minus s, all over b minus s, because the sign between a minus s and concentration of b minus s is minus. We turn to division, bring them under the same one log. Then times, because there's plus sign between ln a minus s minus ln b minus s, plus, that plus turns to sign. Then ln b minus ln a becomes ln b over a. You can see that. Multiply them together, we now have one common simplified expression. 1 over a minus b, b bracket opens, ln b into a minus s, then all over a into b minus s. Then changing that ln to log, we can now have 1 over a minus b equal to 2.303 log b into a minus s, all over a into b minus s. We know that in mathematics that ln of a number is 2.303 log of the same number. So having done that, we go back to equation 2 and integrate this expression k dt. Yes, if you integrate k dt, you still get kt, as we explained before. So we now apply the limits t equal to t and t equal to 0. Replace t as t and replace t as 0. We have k into t minus 0 giving us kt. We now equate the left hand side and to do the right hand side. And the right hand side, the left hand side is this one we have already done. That is, any of this, we equate it to kt. So that gives us 1 over a minus b, 2.303 log b into a minus s, all over a into b minus s equal to kt. So this is the integrated form of a second order reaction of a second order biomolecular reaction involving two different reactants. So you can also subscribe to the channel, tap on the channel, share our videos to students in tertiary institution, let them appreciate the channel, subscribe to the channel and learn more from distant, from far distance, and from nearby. Anywhere you are, you can learn online and understand. Thank you for listening.